Welcome to Lecture 9.1, Object-Oriented Programming Continued for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you'll have an understanding of what object arrays are, how to create and work with object arrays, what inheritance is in object-oriented programming, and applying that to beam bending problems for your later Statics 2 course. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. We've used arrays before in this course. For example, linspace arrays. An object array works exactly the same way, except that each element is an instance of a class instead of just a number. Consider the class that we defined in the previous lecture. A 5-element array would just have 5 different objects of MaterialSample. Now, considering the following array of objects. It's an array of 3 MaterialSample objects, each with slightly different areas. Just like normal arrays, this one can be indexed for each element. We access the first element using the index 1, and we see each of its properties listed out. Notably, the area here is 1 square centimeter. The second element has an area of 4 centimeters squared, and the third has an area of 9 centimeters squared. Now, manually populating this array is tiring, so there are 2 really easy ways to create an array with many instances of a class. First, append the .empty command with 2 size dimensions to the end of the class name, and second, to initialize the first element as an object and then to append more iteratively. We'll cover both of them in this lecture. First, we can initialize space for 100 total instances as follows, using the empty command with the size dimensions 0 and 100. Note that the 0 is necessary here because the array doesn't actually contain anything yet. When we initialize the elements with specific values, this dimension will change to 1. We can loop over that array to initialize each of those objects with slightly different properties by defining first a linear array of areas from 1 square centimeter to 9 square centimeters, just like before, and then looping over the array of objects to initialize a MaterialSample object using those different areas. This fully populates the array of MaterialSample objects called samples. Now, the slower alternative is to grow the array one object at a time. Just like before, define the areas array and then write a loop to initialize the samples array with a new object. The difference here is that we haven't already defined the samples array, so each iteration adds a new element onto the end. Both of these methods produce the same exact array at the end. Now, the dot notation accessor can still be used on the entire array to return an array for all of those values as seen here. We use the .a accessor wrapped in square brackets to return a vector with all of the areas for each object in the array. We can also automatically apply the axial loading function from that class to each of the objects using a loop. I do this by defining an empty array for the post-test samples and then iteratively testing each one inside of the loop. You could totally just operate on the original array and it would work too. This loop constitutes performing tensile testing on 100 different samples for easy behavior analysis. This is much easier than doing the math 100 different times manually. Now, to graph these results, we can get the new lengths of each sample and then calculate the strain values, and then we can also just add some plotting commands. This produces the following figure. Here we see the inverse relationship between the strain and the cross-sectional area. Now, inheritance as a concept enables classes to adopt properties and methods from another class. This is fantastic when you have to create several slightly different classes for something that all share common properties or methods. For example, a beam would contain some general implementations for beam bending behavior, but there are different beam cross-sections out there, so evaluating the specific cross-section properties should be handled separately. Now, you'll get to this in Statics 2, but we're going to implement the deflection equation for a simply supported beam like this, and the equation is as follows from the left end to the force application at A. Now, the beauty of this problem is that the deflection equation itself does not vary for any specific cross-section properties. Only the value of the second moment of area I varies in this case, and that should get handled by each of the individual subclasses. We'll see how that works in a minute. Therefore, we can implement this general equation directly into the superclass. First, the constructor for the superclass should be left empty. Here, because of each of the subclasses will have its own implementation for the properties, we leave it completely empty. Then we can write a general function for the deflection equation from earlier. First, we can write an anonymous function to represent the math equation itself, then define an X array from 0 to the application of that force at A, because that is the domain where the equation is valid. Then follow that up by evaluating the deflection function for that X array. But then we have to do the same thing for the opposite side of the beam. This step is necessary because the equation from before is only valid from the supported end up to the applied force. So we have to solve it in two sections like this and then combine those two domains together. We can then write a generic bend beam method just as an added abstraction layer because this is what the quote-unquote user will actually interface with. This function just calls the beam deflection function that we just wrote, followed up with a plot beam function that we'll write next. I'm not going to review these commands, but it plots the beam and the applied force location. So now we can actually talk about the specific types of beams. First, we have the simple rectangle, where the area and the second moment of area are both very simple to calculate. Now there's also a circle, which also is not very complex, but there's also the I-beam. This is a very common cross-section for things like structural members in buildings. Each of these types of beams can be defined as a distinct subclass of the more generic beam superclass. For the sake of conciseness, we'll only consider the rectangle in this lecture and we'll leave the others for extra practice if you're interested, but they're all basically the same thing. Now, to inherit from another class, we use the left angle bracket operator as follows. Note that the properties include B and H, which are the base and the height of that cross-section. All of this enables this class to use the properties that are defined in the beam class E, A, L, and I, as well as B and H. The constructor for this subclass has to then accept enough inputs to define the properties from both the beam superclass and this rectangle beam subclass. So we write a constructor that accepts the Young's modulus, the length, the base, and the height for the beam. E, L, B, and H can all be directly assigned for the object, but the area and the second moment of area both get derived from the cross-section properties B and H. This constructor right here is the only part of the implementation that really has to change for the other types of beams, and specifically calculating A and I is really the only thing that has to change. Now this inheritance structure enables us to make a rectangle beam and then to deflect it as follows using some of those superclass methods that we wrote before. First, we just define some properties for the beam and then create the beam itself, which we'll call the constructor that we just wrote, and then finally apply the beam bending function with that applied force. This produces the following graph. It shows the deflected beam profile given the force application at 90% of the beam's length, which is shown with the red line. This is very easy to use. Now, in summary, object arrays are a storage device for maintaining many instances of a particular class. They can either be created manually, which is very tedious, or automatically by using the empty method or by iteratively appending another object to the array. Specific objects within that can be accessed by indexing through the array, just like normal, like we've done before, and methods and property accessors can also be applied automatically to the entire array as well. Now, inheritance is an approach for defining multiple classes that would all share common properties and functions such that those commonalities are stored in a superclass, and then each subclass contains only the implementations that are not shared with other subclasses. Beam bending is a perfect example of this because the high-level behaviors of beams can be abstract in the superclass, and the specific implementation of calculating properties like area and second moment of area should be contained within each subclass.